I'm currently constructing a very high-powered laser that I'm going to be demonstrating and showing you how to build in an upcoming video. But once it's complete and assembled, it'll be more difficult to show you a very important aspect of its construction: cleanliness. Now before you go, oh, boring, click, hang on just a sec. Dirty optics have a much broader impact than just on lasers. Microscopes, telescopes, binoculars, rifle scopes, camera lenses, even eyeglasses suffer significantly from dirty optics. When light passes through a dirty lens, it scatters, decreasing contrast. Some of the light is absorbed, decreasing brightness, and the dirt can damage optics. This is particularly true in lasers where the light fluence can easily exceed 1,000,000 watts per square centimeter. The optics can survive that, but when that kind of intensity passes through a dirty lens, it can literally cook the dirt onto the surface, damaging the coating, and if enough heat is transferred, fracturing the optics. Dirt loves optics. Optics hate dirt, and dirt is everywhere. If you wear glasses, you notice after a couple of days, you start playing games with the smudges. You take them off and you're astounded at how dirty these things are. And I swear, I never touch them. Dirt is everywhere. And the problem with dirt is it's a generic term. It's not just fingerprints and oil and lint or minerals left behind by using tap water to clean them. It also includes grit and abrasives. And so even the process of removing dirt can damage the optics. There are three aspects to this. First, the optics themselves. You have to get them clean and you have to keep them clean. Second, the optomechanics, the hardware that supports the glass or the lenses. If this is dirty, it can shed dirt onto the lenses, contaminating them. And finally, the putting everything together, the assembly, has to be done without contaminating everything. Now, before we get into this, I want to make a special announcement. We're going to be adding a new feature to our channel. We're going to continue to upload our science and technology videos just as we have before, no change there. But between uploads, we're going to begin doing live streams, real-time interaction, where we have a chance to talk about science, technology, sometimes current events. We can go through some of the topics that we've covered in previous videos, as well as discuss future videos and other types of technology. We can answer your questions and basically talk about anything that you find interesting. I'm really looking forward to this because I think it's going to be a lot of fun. Now, keep your eyes open because a few days before each of these uploads, or these live streams, we're going to post a notification so that you have a heads up. And with that, let's get started. All right, if you obtained your hardware directly from the manufacturer, it's all nice and clean and bagged up, you're good to go. But if you've had components that have been laying around for a while, even in a drawer, or you're working on a currently operating optical system, there's a good chance you're going to need to clean them. One caveat is avoid the temptation to disassemble these components. Many of them require special techniques and tools in order to reassemble them. And there's a good chance you may damage them when you try to put them back together. The second point is avoid the temptation to submerge or soak these components in a solvent. They have grease and oils that allow them to operate. And when you submerge them or you soak them in a solvent, you can extract the lubrication from where it needs to be and deposit it where it shouldn't be. Now, the first thing you're obviously going to want are some gloves. This will protect you from the solvent, but it will also protect the hardware from your dirty fingers. The next thing is get some canned air. And you're going to look at the part, inspect it, and find the worst culprits. And then over a garbage can or off the table, just judicious puffs of air. Use this sparingly. Avoid the temptation to just lay on the valve like this. This liquid inside will cool off very fast. And if you spray cool vapor or even the liquid at the hardware, you can refrigerate it. And that will allow room humidity to deposit, forming a water film which can attract or stick airborne dirt. So just a few puffs and that's it. Then Q-tips or cotton swabs. These are the cheap kind that we got from the drugstore and they work very well. You can obtain specialty swabs of all different sizes and shapes made for this purpose from optical supply houses like Edmund Optics or Thorlabs, or from industrial supply houses like McMaster-Carr. They're nice and they work well, but they're substantially more expensive. And you're going to do a pretty darn good job with the simple Q-tips. That's all I ever use. Toothpicks. The wood will stick much better to the dirt than to the hardware. And because they're nice and pointy, you can dig into the little nooks and crannies and dig out the little dust particles as well as the dust bunnies that can sometimes wrap around the lubricated components. Then throw this out. Paper towel. You can use a lint-free rag for this purpose, but there's a big advantage to the paper towel. It's really cheap. Because the principle here is we're not trying to just take a cloth and smear a solvent around the surface. We're not trying to decontaminate these parts. We're trying to transfer the dirt from the part to the garbage. So when you use the paper towel and you notice it's starting to get a little bit dirty, toss it and grab another sheet. This is a much better way of getting this clean. Solvents. There's a number of different cleaning solvents you can use, but a very good combination is a 50-50 mix or 1-to-1 ratio by volume of acetone and methanol. This will dissolve just about anything that can stick to this hardware, and the methanol will extend the drying time of the acetone, giving you a little bit more time to work. Do not use the cheap stuff that you get from the hardware stores or the big box stores. This stuff isn't even technical grade. It can be recycled material. It can contain an unknown amount of other non-soluble hydrocarbons that will deposit onto the surface. And when it dries, it can leave an oily film behind and your part can end up dirtier than when you started. For this purpose, you want to use spectroscopic grade solvents. These things will cost you several times more, but when they evaporate, they leave absolutely nothing behind, and you won't use very much of this stuff. When you're dealing with very expensive components like this, you really should go top of the line. Good sources for these chemicals are Lab Alley, Carolina Chemical, and ChemSavers. They all have very good prices, good service, good delivery, and high quality. I've used them all the time. Now, I'm not going to show you how to use a piece of paper towel. I think you can figure that out. But once this is as clean as you can get it, then take an air bulb like this and just blow off any of the lint that might have been left behind by the paper towel or the Q-tips. Because there's nothing left to stick that lint down to the surface, it will come off very easily. There's a reason you don't go back to the canned air at this stage, and I'll explain why in just a sec. Once your part is nice and clean, put it in one of these Ziploc bags, seal the thing up, and you're good to go for your next stage. Now, let's step back for just a second and assume that you manufactured the parts yourself in a shop. The nice thing about that is you're going to have disassembled components, which makes it a lot easier to clean them. But you're also going to have a whole nother order of magnitude of dirt. You're going to have metal chips and cutting fluid and lubricants and oils. They can be a mess. Now, if your shop has a parts cleaner, use it. But if you don't, get yourself a tub like this. This is $4 from Walmart. It's a kitty litter bin, a new one. And fill it with water. And at this stage, it doesn't matter what water you use. You can use tap water, well water, doesn't matter. And dish soap. Grab yourself a toothbrush, some bottle brushes, a sponge that has a smooth and an abrasive side that allows you to really scrub down on the parts, and pipe cleaners. These are excellent for getting into the little nooks and crannies and into the threaded holes that allow you to spin them inside of the holes like this. And you can pull out a fair amount of dirt that you otherwise would not be able to rinse out very easily. You can see right like this. Now, if the holes are larger than these small holes here, but still too small for the bottle brushes, you could grab several of these things, or you can simply fold them like this to make them thicker. And then when you screw them around inside of these larger holes, like this, you can pull out a lot of grease. It works very well. Avoid the temptation to work at the surface so you can see what you're doing. You kind of want to do it that way. But the problem is, especially with the toothbrushes and the bottle brushes, you can spritz a lot of this dirty soapy water all over your clothes and your glasses. Work completely below the surface, submerged. What you're trying to do here is debulk the part. Get rid of, say, 95% of the dirt and set yourself up for the definitive cleaning method, ultrasound. Now, I know I've promised in previous videos that I would go through the assembly and the design of this. I built this thing myself. But for now, I'll just sort of give you the rough parameters. This is an 8-liter unit with a basket so we can put our parts in it. It uses 400 watts of ultrasound, has a heater, and operates at 40 kilohertz. That's a good mid-range frequency for cleaning parts. Almost all optomechanics are going to be either stainless steel or aluminum. If you're working with stainless steel like I am right here, you need a good cleaning solution, and an excellent solution for stainless steel is dilute sodium hydroxide, a detergent, and a surfactant. You could obviously mix that up yourself, but it's easier to just get one of these concentrates. This is one example, Purple Power. I think there's another one out there called Mean Green. There's probably half a dozen different generic names for the same combination of chemicals. If you have any doubt, just look at the ingredients on the back of the container and make sure it's got those 3 components, a surfactant, a detergent, and sodium hydroxide. Now, you can use this stuff full strength, but you can also use it at a 1:5 dilution, and it works just fine like that, and that's the way I always do it. Now, for this step, you're going to want to use deionized or at a minimum distilled water. And we're going to be doing this at a 5:1 dilution. So we're going to put in 4 liters of distilled water. And then we're going to add to that 800 milliliters of the concentrate. Right here. Don't worry about mixing this up. The ultrasound will mix this up in about 100 milliseconds, so we're good to go. Now take your parts, fill your basket. Space them out like this. Lower it into the ultrasound. Then I got to plug this in. We're going to turn it on. Turn on the heater. And a really nice feature of this particular unit, listen. It's almost silent. And that's really nice because that buzzing can be very annoying. And if you're doing several cycles or several batches, it can drive you crazy. Now, you're going to run this to 75 degrees Celsius or 170 degrees Fahrenheit for half an hour. If the parts are aluminum, or you're not sure, lose the sodium hydroxide. It can be corrosive to aluminum. And in that case, the best choice is good old dish soap. You'll use it at the same concentration and the same duration and the same temperature. And when the parts come out, they come out extremely clean. Now, I'm not going to make you wait for half an hour just to let this buzz in front of the camera. So let's assume half an hour has passed. Turn this off. Turn off the heater. And now this would normally be too hot to touch. So you'd grab a couple of gloves and you would pull out the basket put it on an absorbent pad like this one, and then you would wait a couple of minutes to allow these parts to get cool enough so that you can touch them. Then we've got to get rid of the soap. Now the obvious thing to do would be to take the part, it's not really hot now, and place it into a large bin of deionized or distilled water, submerge it, and just rinse it around like this. Really what we're doing when we're rinsing it is we're diluting the much lower volume of soap that we took out that was adherent to the part in the much larger volume of water in the tub, say 1,000 to 1. There's an old saying, the solution to pollution is dilution. Now this works, but there's a better way to do this. If we take 3 smaller containers, each one say has 1/10 the volume of the big tub. If I take a part out like this and I put it inside of this first container, I will dilute the soap 100-fold. When I take it out, I will dilute what comes out 100-fold and then 100-fold. This is exponential. 100 times 100 times 100, or a 1,000,000-fold dilution using 1/3 the amount of water. It's a better way to do it. Now, once the part has come out, you want to place it inside of a clean bin like this. Put the top on and don't snap it down. And in about a day, the part will be super clean and nice and dry. Now, in our situation, we're going to be exposing these components to ethanol, ethyl alcohol, in the laser. So what I did is I filled this container with some spectroscopic grade ethanol, and I am submerging the parts under the layer of ethanol. Then the concept is anything that could have survived this cleaning operation and could be extracted in the laser by contact with ethanol is removed here first. And that's it. Now, optics. If you take away just one fact from this video, I think it should be this: never wipe optics. It's almost always a bad idea. The very method for forming those optics in the first place was to drag an abrasive back and forth across the surface to grind away the glass, and dirt is abrasive. Now, there might be one very small exception to that, and that is if, say, you cleaned off your glasses in a sink and you've got a whole bunch of water droplets on them and you don't want to drive 2 hours down the highway with these droplets in front of you, waiting for them to evaporate. If you have to get the water off, dab or push in order to pull the water away from the surface. Now, this could still damage the optics if you have a little piece of abrasive, but it will be a point defect rather than a long permanent scratch across the surface. There's also a technique I've seen online in several places, and actually in a pretty high-end optical shop. I don't like it, but this is what they recommend. If you want to clean off a lens, you take the lens and you get a piece of very clean, fresh lens tissue like this. And while supporting the lens, you place the lens tissue across the surface of the lens like this. And then wipe it down, rinse it down, get it nice and wet with a solvent like isopropyl alcohol. And then slowly and carefully drag it across the surface. The problem with this is that if there is any kind of an abrasive or a piece of grit underneath there, all you're doing is slowly and carefully grinding a groove or a scratch into the optic. I don't like it. I definitely recommend you don't do that. Now, if you want to clean off the optics and you want to be a lot more gentle, a better technique is to take the solvent. Isopropyl alcohol is excellent. You can use the acetone and methanol mix, and over a large basin, just spray a high velocity flow of the solvent across the surface. You're going to use substantially more solvent to do this, but this is a lot more gentle than having actual mechanical contact with abrasives that may be on the surface. But you can still damage optics this way. There is an optical fabrication technique called magnetorheologic polishing, where they take an abrasive slurry that has ferromagnetic properties, iron-based, and they will pump or flow this abrasive liquid across the surface, and using magnetic coils that can vary the pressure of that liquid on the surface, forming, figuring, and eventually polishing the surface. It's a great technique. But the bottom line is, even when the abrasive is in a liquid form or rolling under a liquid flow, it can still cause abrasion. I mean, that's how the Grand Canyon was formed. Now, another technique is to use ultrasound. It's used all the time on jewelry and on optics, but there are a few caveats. Number one, you don't want to use a unit like this. You want to use a much higher frequency, a minimum of 100 kilohertz. Counterintuitively, the higher the frequency of the ultrasound, the gentler the action, the smaller the bubbles. And you want to watch out for high temperatures. With plastic molded optics and some coated optics, they don't do well at high temperatures. Be aware that although ultrasound is very effective, it's surprisingly aggressive. So you have to make sure you're using the right equipment. In my experience, I think the best method for cleaning off optics is probably the simplest. Get 4 containers like this. Fill up the first 2 with deionized water, and then fill up the first of those 2 with, you guessed it, dish soap. Then in the third container, spectroscopic grade isopropyl alcohol, or you could use acetone and methanol, and the final deionized water. Simply take the optical element, the lens or the mirror that you want to clean off, and submerge it into the liquid. You want to warm these 2 containers in a microwave for a couple of minutes to about body temperature, or no hotter than you can put your fingers in, and just submerge this like this. Now, you don't have to move this around very much, and you want to leave it in there for a few seconds to a few hours, typically a couple of minutes. The only motion that's really necessary at this stage is just to make sure that there are no bubbles that are shadowing the surface. You want to have full contact between the glass and between the liquid. And then after it's been in there for a couple of minutes, then you're going to transfer this, and it's generally a good idea to use a different glove so you get the least amount of soap into the deionized water here. Now you can afford to be pretty vigorous in your motion, because any particles that may have been on here, almost all of them have already fallen off in here. Then after you rinse this off a couple of times, you're going to place this in the isopropyl alcohol. Now, the reason you warm the first 2 containers is because of the same principle that makes it easier to take olive oil off of a spoon than lard. You decrease the viscosity of the oils and the greases, and at the same time you make the soap more capable of solubilizing that grease or that oil. Now, when I go into the final and 4th container, you want to get a good look at the surface of the glass. You'll see kind of an interesting feature on the front surface. Ready?
Yep.
All right, here we go. Watch the front. See those little ripples or waves that form on the surface? That is the isopropyl alcohol being dissolved off into the deionized water. You do that a few times like this, and eventually, when you see those ripples disappear, you're done. And that is a very clean optic. Now, these coatings are extremely hydrophobic. So even if they're super clean, you can still get little water droplets forming on them. And the problem with the water droplets is they can act like a glue to adhere airborne dust. So you want to get them off. And in this case, you want to use your air bulb. So just puffing across the surface like this, remove the water. And that is a very clean mirror. Now, the reason you don't want to go back to the canned air for this process, you've got a good image of that?
Yes.
All right. See the surface now? That won't evaporate. There are hydrocarbons inside of here that are non-volatile and can contaminate optical surfaces. When you use canned air, you only want to use it for the very crudest levels of... It's not dirty? Why are you looking at me?
I was just looking.
No,
I wasn't looking at you. I was looking at it.
No, it looks pretty funky to me. There are... there are hydrocarbons in this can that won't dissolve off. They won't evaporate off. And so if you're going to be cleaning anything off, like I said, you want to do this only on the very crudest levels of cleaning. When, say, for example, you're blowing off your mounts for the first step. After that, you always want to stick with one of these air bulbs. These things, $4 on Amazon, they will never run out of propellant, and they're very clean. This is what you use for optics. Now, one problem you may have is that you might not be able to remove the component from the hardware. Just for whatever reason, you can't get it out. And the problem is you don't want to submerge the components in liquid like this because the liquids could get trapped in the grooves and between the optic and the hardware. And so this is a super big problem for the world's largest telescopes. With mirrors the size of tennis courts, it's extremely risky to disassemble them and transport these mirrors to a special facility where they clean them off. They have to clean them in situ. So what they do is a very interesting technique. They use a device very similar to a fire extinguisher. They will flow extremely clean carbon dioxide right at the surface of the mirror. Carbon dioxide is an excellent solvent for both polar, meaning water-based, and non-polar, oil-based contaminants. It's the reason carbon dioxide is used in high-pressure supercritical extraction devices that are used to take aromatics out of plant matter, seeds, flowers for medicinals and perfumes. But the real secret is because that stream of liquid is extremely cold compared to the surface of the mirror. And as it gets very, very, very close to the surface, it vaporizes. And in doing so, it rockets away, carrying the dissolved components as well as the particles away from the surface. And due to a principle called the Leidenfrost effect, which is what I was able to demonstrate in the last video where I poured liquid nitrogen right onto my hand, the liquid never touches the surface of the mirror. That vapor layer that is constantly being replenished by pure CO2 provides an insulating layer or a protective barrier from all those particles and the snow that are rocketing away from the surface. Now, the only caveat is you can't do this under very humid conditions because as you cool off the mirror, it could condense water vapor. But they generally are cleaning these mirrors during the day when it's dry, and they're also doing this on mountaintops like Mauna Kea and in Chile, where the relative humidity is extremely low. This is a very effective technique. The problem we have is we don't want to invest thousands of dollars in that kind of hardware to be able to clean small components. We got another alternative. It's a product from Photonics Cleaning Solutions called First Contact. Now, they don't sponsor this program, and whenever I buy this stuff, I pay full price for it. I just like it, and I've used it for over a decade. The way it works is it looks a lot like a red nail polish, and it contains solvents and polymers. The solvents will remove the solubles, and the polymers will eventually dry to form a tough rubbery or plastic membrane on the surface of the optic. You simply drizzle it over the surface, let it dry, and peel everything away. It really works. So let me show you how. I have a couple of laser mirrors here, and I'm going to do something that is probably a first for YouTube. All right. Don't ever do this to laser optics. Okay. Now, the way you get this off is pretty simple. You take the polymer and you take a little eyedropper, and you're just going to put a coating of this liquid onto the surface like this. It's quite easy. You don't want to touch this with the dropper. And the only mistakes I've ever made in using this is I've either been impatient and tried to take it off before it fully cured or dried, or put on so little that there wasn't enough solvent to dissolve all of the solubles, or the liquid or the membrane ripped when I pulled it away. But in that case, it's not a problem. You can just simply drip on some more of the liquid. It will dissolve into the old layer and thicken it up. Or you could simply redo it. Just like this. It's kind of fun. I want to get it all. Okay, I think that's pretty good. Now, here's the point. You need to wait about 30 or 40 minutes in conditions like this in order for this to be dry enough to pull off. But you could wait weeks. This acts as a protective barrier and keeps the optics clean and protected from scratching. And so you could transport this, store this with this coating on, and then when you're ready to use it, simply peel it off. The stuff is pretty neat. So let's give this about 45 minutes or so to dry, and we'll see how it works. All right, it's been about 45-50 minutes, and the way that you take this off is the company supplies these little self-adhesive tabs, and you peel them off the backing. You can use Scotch tape for this. I found it works almost as well, but the idea is you simply place it.
Can't really see it with your hand there.
Like there. Just press it down. I'll do the other one now. And just make sure it's contacting all around the edge. I find that's important too. And then we'll see if we can get this off the first time. Got a good scene, a good view of that?
Yeah, keep it there though.
Okay. Now, come on, work with me. There we go. It can sometimes be a bit of a hassle, but that's a clean optic. And now we'll see if we're 2 for 2. Let's press that down a little bit better this time. And like I said, if it doesn't come off the first time, doing it again really is not that difficult. And as you can see, I didn't get some of the agent right near that one edge, and I would probably do that one again because I probably missed a few bubbles there. But you get the idea. Like that. Now those optics are clean. They're atomically clean, and with the little periphery around there, you could add a few drops, but the way to really make sure that you get it clean is you would do another application of the agent across there, because if you try to do just the edge, you're likely to touch it with the adhesive tape and you'll contaminate the optics. These optics are so clean that this material is used both for space qualified optics as well as at LIGO, the Laser Interferometry Gravity Wave Observatory, where arguably the very best optics on the planet are located. This stuff really does work, and it really is easy, and it doesn't produce very much dirt, and I've used this probably several hundred times, and I love it. So look into it if you're interested in cleaning off optics. So now we've got clean mechanics, hardware, optomechanics, and we've got clean optics. We've got to put everything together. And the problem is, from an optical standard, this room is filthy. Wooden walls, wooden ceiling, concrete floors, maybe even a spider web in the corner. And if I was to just hunker over a table and start putting everything together, there's a good chance that we're going to get contamination. Now, if I had a few $1 million or somebody gave me access to a clean room, great. But we can get damn close for a few bucks. Let me show you how. So the first step is to wipe down the surfaces that you're going to be working on right before you're going to start, so that you get the least amount of dust settling on those surfaces. And then once you've finished getting that nice and clean, take some water, tap water, well water, doesn't matter, and start spraying the floor all around the area where you're going to be walking. The idea here is that if there is any dust or debris on the floor, as you scuff across the floor, you're less likely to churn that dirt up. It's a temporary glue for dirt. This is also pretty useful to use if you're in a woodworking shop and you want to do a final stain or a finish and you want to tamp the sawdust down. It works. It's nice. And then when it's dry, it doesn't leave any more on the floor than you started with. Then go to the hardware store and get the cheapest piece of drop cloth you can find. And when I say cheap, I mean the thinnest piece. If you can find the clear material, the old stuff, that's even better. But even this more milky material will work very well. And then you're going to need an assistant, because what we're going to do is we're going to build a little tent here. You want to take this side and we'll start doing the unroll here. Like that. And then we're going to open this up. And the old clear stuff was harder to work with, but it actually works a little bit better. I'm working on this part right here, all right? Oh, that's pretty good. Let's start going over right now. Let's just keeping it off the floor. Like that. Now I've got a fair amount hanging off here. How much do you have on your side?
Pretty much just reaches the table.
Take about a foot. Take about a foot more. Just pull it toward you. Oh, that's not bad.
I think I still probably have a little bit more than you. I can go a little bit more.
All right, take just a little more. That's pretty good. Okay, you're good. Now we're going to put a couple of clamps on the corners here. And what this is going to do is just weight it down to stabilize it so it doesn't pull and fall down on my head. And I think this side here needs a little more unfolding, like this. Yeah, that's it. That's it. Just my side now. Good. Then I'm just going to draw this back a little bit. Bring this out so I got a little more room to work.
How's that?
That's pretty good. And then I think it just moved the, yeah, stretch that. It's pretty good. I like this. Yeah, that'll work. That'll work here. Okay. Now, you might think that this ain't a bad idea. Forms a tent, keeps the dust from settling on top of you. But the real magic is actually more subtle. Have you ever used cling wrap, this sort of stuff, and you're going to try to wrap some food, and as soon as you peel this off and you're going to try to put it over the bowl, you start swearing and cursing because it's all sticking to itself? Part of the reason that happens is because as you unroll the plastic and move it through the air, you generate a static electric charge. This is particularly noticeable when you use a vacuum to suck up plastic powder or packing peanuts. You can actually get a static shock. The potential generated across the surface of the plastic can be very high. And what that does is it attracts dust, both outside and inside. It acts a little bit like a getter in a vacuum pump. It attracts and then holds onto dust that might be present inside of the chamber or the tent. And this is much better than using, say, a HEPA filter or even an ULPA filter in a room like this. Because the problem with those filters is they can produce an extremely clean stream of air. But because that air is moving, according to the Bernoulli principle, the pressure of the air inside of that stream is lower than the static air around it. So it will entrain the room in the air in the room along with the dust, giving you a dustier stream because some of that dust never even saw the filter. Those filters will work very well, but you have to be in an already very, very clean room. So now that we're set up, I've got to get changed. Now I'm going to get inside. Okay. Now a couple of pointers. Number one, this tent, this enclosure, is a one-time use because as the dust gets attracted to the surface and it loads up, eventually you'll reach equilibrium where the dust will begin shedding as quickly as it's attracted. So after you've finished your project and you've wrapped everything up, everything is assembled, then go ahead and throw this out. This is a one-time use. Or if you're going to save it for a painting project or something a little bit less demanding. The second thing is, do not do any type of high-tech or delicate electronics work in here. The voltage potential across this plastic can be substantial and it can damage very small microscale electronic components. It can undermine the advantage of an ESD or electrostatic discharge mat. So this is good for optics, not so good for electronics. And finally, do this when it's very cool, or better yet, at night. First of all, your neighbors won't be looking in the window wondering what the heck you're doing, but also with this tent and the stagnant air and the additional layer of cloth, you're going to get pretty hot. Now you could go commando, but we won't ask and you don't have to tell. So hopefully you found this interesting and potentially useful. And if you like the kind of stuff that we're doing on this channel, please take a few seconds and subscribe. It really helps us out because it helps promote our videos through the YouTube algorithm to a much broader audience. And the bigger we get, the more we can afford to show you. And remember, like I said at the beginning of the video, keep your eyes open for our notifications for our first and the beginning of our series of live streams. I think that's going to be a lot of fun and I'm really looking forward to it. We're also hoping to punch through 1 million subscribers this year. So with your help, I think we're going to get there. And with that, I will wish you a very good evening. You take care, stay safe, and have fun.